In this video, we'll be looking at an example of volumes by attachment. In this specific example, we're looking at squares, and those squares will be parallel to the y-axis. So our first step is to actually graph the region that we're identified. Y equals x minus, or negative x plus 1 is going to be a value shifted up here and plotted like this. And then we're also contained by the x and the y-axis. Now, the way that I've drawn this way too small for us to see anything, so let's take that object and blow it up outside here. Okay, this here is again that original function y equals negative x plus 1, and then we're going to have again the x-axis and the y-axis as other bounding functions. Now the next step that we're going to do is we're going to go ahead and visualize attaching the squares that are going to be parallel to the y-axis. In other words, we're going to go ahead and draw in at least one square where the distances here are as accurate as possible. So that'll be the one square that we attach, and if I try and do another one here, again, notice that that square is going to end up getting a little bit larger. And we're going to go ahead and just simply continue to attach all these squares. Now, some of them are going to be smaller than others, and some of them are going to get really close to the edge. So this is the idea of what we're looking at here. Now, to do this accurately, we're going to have to integrate some kind of area function. And I'm going to go ahead and write area dx, because we know it's in terms of dx given the fact that it's sliced vertically. All these attachment of these squares end up being, again, vertical attachments. Now, if they were attached horizontally, that would be a different story. We'd want this in terms of dy. So I'm going to try and figure out what my bounds are in terms of from x to what to what. Well, in this case, since I'm starting here at the x equals 0 line, the y-axis, I'm going to go all the way out to this location here, which if I try and intersect y equals 0, which is, again, this line here, with the line y equals negative x plus 1, you'll notice then that I'm going to have x equal to a positive 1. So these two together give me this intersection point of 1, 0. So I'm going to start at 0 for x, again, because of this location right here. And I'm going to end at the x value of 1. So that's going to be the bounds on this area. Now again, recall that we're trying to integrate over an area function in order to make this thing have a volume. Now if we were to go ahead and just find the area of this object, if we were to go ahead and find the area of this region, we would go ahead and integrate just over this function right here. But because we're looking for a volume, the volume equaling to the integral of an area, we're going to go ahead and set up our area formula. Well, the area formula for this object is that we're attaching squares. So that means that this length right here, which again in the previous video I might have called s, that distance right there is this. That distance there, if I square it, will end up providing me with, again, x minus 1, negative x minus 1, or negative x plus 1 times negative x plus 1. If I square that function, this is the actual area at any given x value in this particular triangle. Again, if I graph myself any single square in this system, that's the area at every single one of those locations from 0 to 1. So this is actually the integral that will provide me with the volume of the space and object described. So my next step is simply to evaluate this integral, which again I'm going to go ahead and at the very least set up. I'm going to square this function, making sure that, again, I write it twice off to the side here if necessary, negative x plus 1 times negative x plus 1, and FOIL this out, providing me with a positive x squared, negative 2x, and plus 1 in terms of dx. And at this point, we're just going to go ahead and straight up integrate. So x to the power of 3 divided by 3 minus 2x squared divided by 2 plus x, evaluated from x equals 0 to 1. If I plug in 1, I'm going to end up with 1/3 minus 1 plus 1, and I'm going to subtract from that. Me plugging in 0 gives me 0 for all those terms. So in the end, it looks like the volume of this object described is 1/3, and now if I were to identify units, if they gave me units, it would be cubic units. So again, the volume of this object described, where if I try to draw out the entire thing, is simply just going to be some kind of squared base pyramid, is going to be a volume of 1/3 cubic units.